On August 15th, 1977, a telescope in Ohio caught a signal so strong the astronomer on duty circled it in red ink and wrote one word beside it: "Wow!" It lasted 72 seconds. It came from deep space, and it has never repeated. Tonight we travel to a star that whispered back at us, an ocean sound louder than a blue whale, a pulse from a dead city of atoms, and a silence hiding inside the cosmic background. If these mysteries pull you in, tap like and subscribe so you don't miss what we uncover next. Get comfortable, the sky is listening too. Jerry Eamon sat alone in a quiet office in Ohio, sipping coffee, flipping through a thick stack of computer printouts. It was 3 days after the signal arrived, and nobody had noticed yet. The Big Ear radio telescope had been scanning the sky on autopilot, printing its findings in tiny rows of numbers. Most of those numbers were ones and twos, the background hum of the universe. But halfway down the page, Jerry saw something that made his coffee go cold. A vertical line of letters and numbers shot up from the noise. 6, EQUJ5. The intensity of the signal had climbed so high the printer had run out of digits and started using letters instead. It was 30 times stronger than the empty sky around it. Jerry grabbed his red pen, circled the column and wrote a single word in the margin. Wow. That word became its name. The WOW signal. Here is what makes it impossible to forget. The burst lasted exactly 72 seconds. The precise amount of time the telescope's beam could sweep across a single point in the sky before the Earth's rotation carried it away. That timing fit perfectly with the source sitting still in deep space, far beyond our solar system, waiting for us to pass through its beam like a lighthouse catching a ship. The frequency was even stranger. It came in at 1420 megahertz, the exact natural frequency of hydrogen gas. Scientists have long considered this the most logical channel any advanced civilization would use to contact us. Hydrogen fills the universe. Any intelligent species studying the stars would know it. If you wanted to be found, you would broadcast there. The signal came from the direction of the constellation Sagittarius, from a region with no known stars, no planets, no obvious source of any kind. It was as if someone had stepped out from behind empty space, spoken one sentence, and vanished. For decades, astronomers tried to explain it away. Could it have been a satellite? No satellite was broadcasting there. Could it have been space debris reflecting a ground signal? The frequency is protected by international law, kept silent for radio astronomy. Nothing on Earth should have been transmitting anywhere near it. Could it have been a passing comet? One team tried to blame 2 icy comets that drifted through that patch of sky years later. Other scientists checked the math and found the comets were in the wrong place at the wrong time. Jerry Eamon spent the rest of his life studying that signal. He pointed the Big Ear at that same spot more than 50 times afterward. He recruited other observatories to join him. The most powerful radio telescopes on Earth have listened to that exact coordinate again and again. For nearly 5 decades now, that part of the sky has stayed completely silent. Whatever sent it has never sent anything again. Jerry died in 2024 without an answer. But before he passed, he told an interviewer something chilling. He said the signal behaved exactly like a message, not like static, not like a glitch. Like a voice that spoke once knew we were not ready and moved on, and that was only the beginning of what the sky has been whispering. 23 years after Jerry Eamon circled his signal, a graduate student in West Virginia made a similar discovery, buried inside old data nobody had bothered to check. His name was David Narkovich. The year was 2007. His professor, Duncan Lorimer, had asked him to sift through archive recordings from a telescope in Australia, looking for pulsars. What Narkovich found instead was louder, shorter, and far stranger than anything anyone expected. A single flash, lasting only 0.005 of a second. In that tiny sliver of time, the burst released as much energy as the sun produces in an entire month. Imagine compressing 30 days of sunlight into the blink of an eye and firing it across billions of miles of space. That is what this flash did. Then it was gone. They called it the Lorimer burst, and it opened a door into a whole new category of cosmic mystery. Over the next 10 years, telescopes around the world began catching more of these quick flashes. Astronomers gave them a name: fast radio bursts. Each one behaved the same way: a short, violent pop of radio energy, gone before you could even register it, coming from places so far away the light had been travelling for billions of years before it arrived. Here is where the mystery deepens. These bursts carry the fingerprints of their journey. As radio waves travel through deep space, they pass through clouds of electrons, and those clouds slow different frequencies by different amounts. By measuring that delay, scientists can work out how much material the signal crossed. Every fast radio burst studied so far has crossed so much space, it could only have come from outside our galaxy. Some came from halfway across the visible universe. What could release that much energy in a single millisecond? Nothing in our current understanding of physics should be able to. A supernova releases huge energy, but spreads it over weeks. A black hole devouring a star takes hours or days. These bursts do it in less time than a camera shutter. Whatever makes them has to be small, powerful, and violent beyond imagination. The theories piled up quickly. Some scientists proposed collapsing neutron stars, objects so dense a single sugar cube of their material would weigh as much as a mountain range on Earth. Others suggested magnetars, dead stellar cores wrapped in magnetic fields 1,000 trillion times stronger than anything we can produce in a laboratory. A few bolder researchers whispered a possibility nobody wanted to say out loud. What if some of these bursts were artificial? What if we were hearing the exhaust signature of alien spacecraft punching across galaxies at nearly the speed of light? For years, this was considered a fringe idea. Then the detections multiplied. Telescopes now catch fast radio bursts almost every single day. Some come from regions of space where no obvious source exists. A few come from nearby galaxies, close enough that future telescopes should be able to zoom in and see whatever made them. Yet something kept making these signals stand apart from every other cosmic flare. They did not follow the rules of one-time stellar disasters. A few of them came back, and when one of them came back, it came back in a way that broke every theory scientists had built. Because one fast radio burst kept repeating. The signal came from a tiny dwarf galaxy, 3 billion light-years away, a place so small and dim that nobody had bothered to map it in detail. In 2012, the Arecibo telescope in Puerto Rico caught a fast radio burst from that direction and logged it with a plain catalogue number, FRB12102. No one paid it much attention. One burst among hundreds, another mystery for the pile. Then, in 2015, it happened again. From the same spot, same galaxy, same fingerprint of matter crossed along the way. That should have been impossible. Every theory at the time depended on fast radio bursts being one-time events, a star collapsing, a neutron star tearing itself apart, a magnetar unleashing everything it had in a single lethal flash. These were supposed to be cosmic death cries, loud and final. Nothing was supposed to survive sending one, let alone send another. FRB-12102 kept going. Scientists pointed dishes at that dwarf galaxy and waited. The signal came back and back and back again. Sometimes it would stay silent for weeks. Sometimes it would unleash 10 bursts in a single hour. By 2017, astronomers had catalogued more than 200 pulses from that exact coordinate. By 2020, the count had passed 1,000. Each pulse was a few milliseconds long, carrying as much energy as the sun produces in a full day, packed into a burst shorter than a hummingbird's wing beat. A team from the Netherlands used a network of telescopes spread across Europe and North America to pinpoint exactly where in that dwarf galaxy the source lived. When the result came in, the room went quiet. The signal was coming from a region only 10 light-years wide, crammed right next to a glowing cloud of ionized gas. That combination told them the source had to be something extreme, something young, violent, and surrounded by the wreckage of its own birth. The leading theory now is a magnetar, a type of neutron star with magnetic fields so intense they would rip the atoms out of your body if you came within 1,000 miles. A magnetar that energetic, embedded in a nebula of its own making, could theoretically burp out radio bursts over and over as its field twists and snaps. That theory has a problem. In 2020, a different team watched FRB-12102 for months and noticed something no magnetar should do. The bursts were arriving in a pattern. Roughly every 157 days, the source would wake up, spit out dozens of bursts across a few days, then fall silent for about 5 months before doing it all again. A cosmic rhythm, a heartbeat, a schedule. Magnetars do not keep schedules. Nothing in the known universe that produces this much energy should be able to follow a calendar. Some researchers propose the magnetar might be orbiting a massive companion star, getting squeezed into bursts as it swings close. Others suggested a precessing neutron star wobbling like a top. A few wondered whether we were looking at something far more ordered than any dead star had a right to be. And in that same year, another repeater appeared. This one ticked with even stranger regularity. Back up for a moment to the discovery that started all of this, because the story behind the Lorimer burst is stranger than most people realize. The data that held it was 6 years old before anyone looked at it. In 2001, an Australian radio telescope called Parkes had been scanning the southern sky for pulsars. The telescope pumped out terabytes of raw recordings, far more than any human could analyze in a lifetime. Most of the files went straight into archive storage, waiting for someone to have the time and the curiosity to dig through them. Duncan Lorimer was that someone. In 2006, the American astronomer handed the tapes to his student David Narkovich and told him to write software that could scrub the recordings for unusual spikes. Narkovich did the work. When the computer finished its first pass, one line leaped off the screen. A burst so powerful and so short it should have set off alarms the moment it arrived. Instead, it had been sitting in a box for half a decade, ignored. The flash had happened on July 24, 2001. It came from the direction of the Small Magellanic Cloud, a neighbouring galaxy about 200,000 light-years away. But the fingerprint of the signal, the slowing it had experienced as it passed through the universe, told a different story. The burst had not come from our neighbour galaxy. It had come from roughly 3 billion light-years beyond it, from a source far outside our local patch of space. For weeks, Lorimer and Narkovich refused to announce anything. The burst was so bright, so energetic, so impossibly brief, they were convinced it had to be a glitch. Some kind of error in the telescope electronics, a truck driving past the observatory, a phone call bouncing off the dish. They checked everything. They checked it again. They brought in other experts. Nobody could find a mundane explanation. When they finally published in 2007, the reaction in the astronomy community was skeptical. A few scientists accused them of mistaking interference for science. Others shrugged and said one weird event does not prove anything. The paper might have been forgotten entirely if a group of Australian researchers had not spent the next several years chasing ghosts through the park's data. That chase produced the embarrassment known as the Peritons, signals that looked almost exactly like the Lorimer burst, but turned out to be microwave oven leakage from the observatory's own break room. For a while it seemed like the whole discovery might unravel. Critics argued the Lorimer burst was just a fancier oven door. Then, in 2013, a different team using a different telescope caught 4 new bursts, all from deep outside our galaxy, none of them anywhere near a kitchen. The Lorimer burst was vindicated. Fast radio bursts were real. Today, more than 5,000 of them have been recorded, and the original Lorimer burst remains special for one reason. It was the loudest single burst ever detected. No event since has come close to matching its raw brightness. Somewhere 3 billion light-years from here, something screamed once, loud enough to cross the visible universe, and was never heard from again. That silence has a name among astronomers. They call it the Lorimer Echo. For a brief stretch of 2004, a small team of SETI astronomers believed they might have found it. The first confirmed alien transmission. The signal was weak, faint enough that most telescopes would have missed it entirely, but it kept coming back. And every time it returned, it behaved in a way no natural source in the known universe had any business behaving. They called it SHGB02+14A, an ugly catalogue name for what looked, for a few tense weeks, like the biggest discovery in human history. The hunt had started in 1999, when a project called SETI at home began distributing tiny packets of Arecibo telescope data to ordinary people's home computers. Millions of volunteers downloaded a screensaver that crunched the numbers while their machines sat idle. When the software found something unusual, it flagged it and sent the report back to headquarters in California. Out of billions of data slices processed, a small handful kept flagging the same coordinate. A patch of sky between the constellations Pisces and Aries. No visible star sat there, no known object of any kind, just empty dark. Yet 3 separate observations spread over 3 years had picked up a narrow-band radio signal coming from that exact spot. A narrow-band signal is the astronomical equivalent of a single whistled note. Nature almost never produces one. Stars broadcast across wide ranges of frequency. Gas clouds hum in broad, fuzzy choruses. A pure, narrow tone is the hallmark of artificial broadcasting. It is the kind of signal we would send if we wanted someone across the galaxy to know we were here. And this one was drifting. Here is where the story gets strange. The frequency of the signal was shifting with time, a slide up the spectrum at about 8 to 37 Hz per second. Under normal physics, a signal drifts because its source is moving relative to us. A transmitter sitting on a spinning planet would show a small, predictable drift from the planet's rotation. A spacecraft would show drift from its engine. But the drift observed in this signal was far faster than any planetary rotation should produce, pointing toward a source spinning around 40 times faster than Earth, or a craft accelerating at a rate no known natural process can sustain. Astronomers pointed the massive Arecibo dish at the coordinate a fourth time to confirm the find. The signal appeared again, but it had drifted so far that it now sat in a completely different frequency. The research team redid their calculations. They double-checked their equipment. They tested every instrument in the chain. Everything looked clean. The news leaked to a British magazine in 2004, and suddenly the whole world was reading about a possible alien transmission from an empty patch of sky. Then came the quiet. Follow-up observations grew thinner. The signal became harder to reacquire. Some scientists proposed it might be a rare natural phenomenon nobody had documented before. Others blamed instrumental noise building up over multiple sessions. A few still suspected something real was out there, drifting and fading as it moved through the dark. 2 decades later, SHGB-02+14A has neither been confirmed nor ruled out. It sits in the SETI archives, a faint whisper from a spot where nothing is supposed to be. On April 29, 2019, a radio telescope in the Australian outback recorded 30 hours of silence, except for a 5-hour stretch when it did not stay silent at all. The telescope was listening to Proxima Centauri, the closest star to our Sun. Only 4.2 light-years away. Close enough that if someone there turned on a flashlight, the photons would reach us in less than 4.5 years. Around that star orbits a planet called Proxima b, roughly Earth-sized, sitting inside the habitable zone where liquid water could in theory exist on the surface. It is the most promising nearby target we've ever had in the search for another Earth. The telescope was part of a project called Breakthrough Listen, a $100 million initiative funded by a Russian-Israeli billionaire with one goal: point the biggest dishes on Earth at the nearest stars. Listen as hard as possible. See if anyone is whispering back. For most of those 30 hours, Proxima Centauri whispered nothing. Then, for 5 hours straight, a narrow signal appeared at 982.002 MHz. It sat there, quiet but persistent, with no drifting, no modulation, no obvious pattern. Just a thin, pure tone from the direction of our closest neighbour. The observation got logged, archived, and ignored for more than a year. In October 2020, a graduate student named Shane Smith was scanning through older Breakthrough Listen data and stumbled on the 5-hour anomaly. He flagged it to the team. They flagged it higher up the chain. The signal got a catalogue name, BLC1, short for Breakthrough Listen Candidate 1. It was the first candidate the project had ever considered worth a second look. The properties made it irresistible, a pure single-frequency tone. No natural source in the sky produces one of those for 5 hours. The signal also showed a small frequency shift consistent with the motion of a planet in orbit, a subtle drift that would make sense if whatever produced the signal was sitting on a rotating world. For a few months in late 2020, a small group of scientists walked around with a secret most of humanity would have wanted to know. They might be looking at a transmission from another civilization, 4 light-years from Earth. They did what good scientists do. They tried to kill their own finding. They pulled out their checklists of terrestrial interference sources. They compared the signal to databases of known satellite frequencies. They looked at what else the telescope had been picking up on the same nights from other directions, and that is where the story changed. The same signal, or something almost exactly like it, appeared in data pointed at totally different patches of sky. A real signal from Proxima Centauri should only appear when the telescope was aimed at Proxima Centauri. BLC-1 was showing up elsewhere too, meaning it was likely bouncing around inside our own radio environment. Some device, somewhere on Earth, was probably broadcasting on a frequency close enough to confuse the instruments. By late 2021, the team announced their conclusion. BLC-1 was almost certainly interference, an unlucky resonance from human technology masquerading as a message from the stars, almost certainly. Those two words haunted the paper. They haunt it still. In September 2015, a Yale astronomer named Tabitha Boyajian published a paper that broke the internet. It was not full of aliens or messages or radio bursts. It was full of light, or rather the strange way a star was losing its light. The star sits about 1,500 light-years from Earth, in the constellation Cygnus. Its official name is KRIC 84628552, a mouthful even for professionals. Everybody just calls it Tabby's star now, after the woman who made it famous. NASA's Kepler Space Telescope had been watching that star for years, along with 150,000 others, looking for tiny dips in brightness that would mean a planet passing in front. A normal planetary dip looks like a small clean notch in the light curve. A circle moves in front of a circle. The star dims by a fraction of a percent for a few hours, then brightens back to normal. Every planet Kepler ever found looked more or less like that. Tabby's star did not look like that at all. The dips were massive. Some reached 22% darkness, meaning something was blocking nearly a quarter of the entire star's light. They were also the wrong shape, no symmetric notch. The dimming would arrive slowly, plunge to weird depths, ripple strangely, and then climb back at a different rate. A planet passing in front of a star cannot make that shape. Not even a giant planet. The biggest gas world we know, Jupiter, only blocks about 1% of the sun's light when seen from far enough away. The dips were also irregular, no clean orbital period. One huge dimming event in March of 2011, a cluster of them in 2013, then long stretches of normal brightness, then sudden chaotic plunges again. Whatever was blocking this star was not on a clean orbit. It was a mess. Volunteer analysts at a project called Planet Hunters had flagged the star first. Boyajian's team spent 2 years checking every explanation they could think of. Was Kepler broken? No, it was measuring thousands of other stars correctly at the same time. Was it a nearby cold companion star dragging dust around? Spectra showed no such companion. Was it the aftermath of a cataclysmic collision between planets? Possible, but the star showed none of the infrared heat glow that such a collision should leave behind. A graduate student named Jason Wright tossed out a wild idea in a paper the following year. What if we were looking at an alien megastructure? A partially completed Dyson swarm, a cloud of solar panels or giant collectors built by a civilization trying to harvest their own star's energy. That shape, he argued, could produce exactly the strange irregular dips Tabby's star was showing. The idea went viral. Scientists cringed, then argued, then listened more carefully. Radio telescopes swept the star for signals. None were found. In 2017, a massive follow-up showed the dimming was slightly different at different wavelengths, meaning the blocker was almost certainly dust of some kind, not solid metal. Tabby's star is now mostly explained as a cloud of uneven dust. Mostly. Nobody has produced a model that matches every dip. The star continues to dim on and off strangely to this day. For 15 years, the Parkes radio telescope in rural Australia kept catching signals that almost, but not quite, looked like fast radio bursts from the depths of space. They had the right sharpness, the right millisecond duration. the right tantalizing hint of deep cosmic origin. There were 25 of them logged between 1998 and 2014. Scientists gave them a name drawn from Greek mythology: Peritons, mythical creatures that cast the shadow of a man instead of a deer, half familiar, half alien, always wrong. The Peritons were a headache. They kept forcing researchers to question whether fast radio bursts were real at all, or whether the whole new field of astronomy had been built on a misread. Here is why the confusion was so deep. A true fast radio burst arrives with a specific signature. Because radio waves slow down as they pass through clouds of electrons in space, a burst from billions of light years away should hit the telescope at slightly different times depending on its frequency. Lower frequencies arrive a fraction of a second later than higher ones. This smearing is called dispersion, and it is a fingerprint of cosmic distance. Nothing on Earth should be able to fake it, except the Peritons were faking it. They showed dispersion patterns that looked startlingly close to real cosmic bursts, except the shape was just a little off. The curve did not quite match what deep space should produce. And more damning, the Peritons only ever appeared at Parkes. No other observatory in the world was catching them. If they were real signals from the universe, other telescopes should have seen them too. A young astronomer named Emily Petrov took the mystery personally. In 2014, she led a team to install new monitoring equipment at Parkes, a device that could detect stray radio interference from nearby electronics. They wanted to catch a Periton in the act. For months, nothing happened. Then, in January of 2015, the monitors lit up at the exact moment a new Periton burst registered in the main telescope. The team rushed to compare the two. The interference matched perfectly. Whatever was causing the burst was sitting right there on the observatory grounds. They walked around the facility with handheld radio detectors, following the trail. It led them straight to the staff kitchen. More specifically, to a microwave oven. When someone opened the microwave door before the timer finished, a burst of radio energy leaked out in exactly the 2 to 3 second window. Because of the way Parkes scanned the sky and filtered its data, that leak looked almost identical to a millisecond signal from billions of light years away. For 15 years, the world's most sensitive radio telescope had been catching lunch breaks. The embarrassment was global. Newspaper headlines made jokes for weeks. Critics of SETI and FRB research pointed to the Peritons as proof that the whole field was unreliable. Then, in the same year, a different paper confirmed that true fast radio bursts were still real, caught by telescopes on the other side of the planet where no microwave could be blamed. The lesson cut deep. Before declaring anything to be a voice from the cosmos, rule out every voice from the kitchen. The Peritons now serve as a warning tack to the wall of every radio observatory on Earth. In 2019, a volunteer team scanning radio survey images from a telescope in Western Australia noticed something nobody expected. A faint, perfect ring glowing in deep space with nothing at its centre. No galaxy, no star, no cloud of gas. Just a luminous circle of radio light, hanging in the dark like a smoke ring from a cigarette that had never existed. They assumed it was a glitch in the data, a processing artifact, maybe a lens flare from a nearby satellite. Then they found another one, then another. By the end of that year, 4 of these perfect rings has been catalogued. By 2022, the number had grown. The astronomers gave them a name as plain as their appearance was strange. Odd radio circles, abbreviated ORC in the literature. Each ring was enormous, roughly 1 million light-years across, bigger than most galaxies. For reference, our entire Milky Way is about 100,000 light-years wide. These circles could have swallowed 10 of our home galaxies and still had room to spare. Nothing like them had ever been seen before. At first, astronomers tried to match them to known objects. Could they be supernova remnants, the expanding shells of exploded stars? No. Those stay inside our galaxy and are far smaller. Could they be planetary nebulae, the shed outer layers of dying stars? Too small again, by a factor of thousands. Could they be the afterglow of ancient gamma-ray bursts, the most violent explosions in the universe? The geometry did not fit. Gamma-ray burst remnants leave irregular shells, not clean rings. A clue arrived when higher resolution follow-up observations showed that 3 of the 5 best-studied rings had galaxies sitting exactly at their centre. Not bright galaxies, not obvious ones. Quiet, middle-aged galaxies with nothing visibly unusual about them. But there they were, centred inside the glowing loops like targets inside a rifle scope. This changed everything. Whatever was making these rings appeared to be erupting from the cores of ordinary-looking galaxies. Something in the hearts of those galaxies had pushed out a bubble of energy so enormous it extended far beyond the galaxy's own edges, and somehow that bubble was glowing in radio light but not in visible light or X-rays. The leading theory points to a galactic collision that happened billions of years ago. When 2 galaxies merge, their central supermassive black holes eventually pair up, spiral toward each other, and slam together. The slam releases a shock wave that races outward through the surrounding gas. Some researchers believe odd radio circles could be the ghostly echo of such a merger, a wavefront of energized electrons expanding for millions of years after the collision itself. Others disagree. A competing theory suggests a massive starburst, an epidemic of star formation inside a galaxy that lit up billions of suns almost simultaneously. The combined solar winds from all those young stars could have blown out a spherical shell so large it dwarfed its parent galaxy. Neither theory has won yet. New radio telescopes coming online in South Africa and Australia are expected to find hundreds more of these circles in the next few years. Each one is a perfect silent ring in the dark, marking the site of some cataclysm nobody yet understands. At the heart of our own galaxy, roughly 26,000 light-years from where you're sitting, sits a monster. A supermassive black hole called Sagittarius A star, weighing as much as 4 million suns, crammed into a region smaller than our solar system. Around it swirls a chaotic storm of stars, gas, dust, and radiation. Anything that wanders too close gets stretched, shredded, and swallowed. For decades, astronomers assumed they had catalogued everything that made noise in that region. They were wrong. In 2020, a young radio astronomer named Ziteng Wang, working with colleagues in Australia, was scanning survey data aimed at the Galactic Centre when his software flagged something nobody had seen before. A faint radio source flickering on and off, sitting about 20 degrees from the black hole itself. It did not match any known pulsar catalogue. It did not show up in X-ray surveys. It did not appear in infrared images. It existed only in the radio band, and it behaved in a way no pulsar or magnetar had ever been recorded doing. They named it ASCAP J173608.2-321635, a catalogue tag derived from the telescope that spotted it and the coordinates it came from. Everyone just calls it the Galactic Centre transient. Its behaviour sits in a class of its own. Here is what it does. It appears, stays bright for a few weeks, then vanishes. When it returns, sometimes months later, the light coming from it has a completely different polarization. the property that describes the twist of a radio wave as it travels. Pulsars show stable polarization. Magnetars drift slowly. This object flips its signature like a light bulb, switching colors between blinks. The brightness pattern is even stranger. Observations have caught it changing by a factor of 100 in a single day. For perspective, most stable cosmic radio sources change by a few % over years. This one swings by 2 orders of magnitude overnight. For the first 2 years after the discovery, scientists debated whether it might be a new type of neutron star. The radio emission was strong enough that some type of compact stellar remnant had to be the most likely culprit. But the polarization behavior kept breaking the models. A team from the University of Sydney ran simulations of every known neutron star variant. None matched. Then in 2022, a second source showed up. Similar behavior, also near the galactic center, also flickering on and off with wildly changing polarization. A third one was reported in 2024. Whatever was happening near the heart of our galaxy, it was happening in multiple places. One emerging hypothesis argues these are a new subclass of pulsars, objects caught in a phase of their life cycle that no survey had ever resolved before. Another theory blames the extreme environment near Sagittarius A star itself. The density of gas, magnetic fields, and gravitational distortion around the black hole might be warping ordinary stellar signals into something unrecognizable. A more exotic idea proposes these transients are the radio echoes of flares produced when small objects fall into the supermassive black hole. Each flicker, a distant siren marking another act of cosmic destruction. Follow-up observations are ongoing. For now, something at the center of our galaxy is blinking in a code no human has learned to read. Early in 2022, a graduate student named Tyrone O'Doherty was using a radio telescope called the Murchison Wide Field Array, buried in the Australian desert, to hunt for slow pulsing objects. The instrument had been built specifically to catch faint, long-period signals from the sky. He was working through old data from 2018, running his detection algorithm across thousands of hours of recordings, when a bright source pulsed at him from a corner of the constellation Scutum. It pulsed for about 30 seconds. Then it went silent for 18 minutes. Then it pulsed again. Tyrone stared at the pattern for a long time. He ran the detection again. He ran it on different nights of data. The pulsing was there, night after night, lasting about 3 months in total before fading away. Every 18.18 minutes, without fail, for a full minute at a time, the object had been bright enough to outshine every other source in that patch of sky. Then, after 3 months, it had gone dark. Pulsars do not do this. Pulsars pulse every few milliseconds to a few seconds, driven by their breakneck rotation. A neutron star slows down as it ages, and at some point physics draws a line. A pulsar rotating more slowly than about a minute should no longer be able to produce radio emission at all. It would cross what astronomers call the death line, a threshold where the star's magnetic field can no longer accelerate particles fast enough to glow in radio. This object was rotating, if it was rotating at all, once every 18 minutes, deep into the graveyard zone. The discovery got published in 2022. The object got catalogued as GPM J1839-10. Within weeks, a global race was on to understand it. The same team pointed their telescope at that coordinate a second time later that year and caught the object pulsing again. Another batch of 3 months of activity, then silence. They dug through historic survey data going back decades and found that the signal has been appearing and disappearing for at least 35 years, well below the detection threshold of old instruments, but there if you knew where to look. Here is what makes this genuinely disturbing for astrophysics. If this object is a neutron star, it should not be able to emit radio waves at all, not with that rotation period. Every published model of pulsar physics says the engine dies when the spin slows this much. Yet here is a source that has clearly been doing it for decades. One hypothesis proposes this is a new kind of object entirely, a magnetar that has evolved past the normal pulsar phase, kept alive by a still unexplained mechanism in its magnetic field. Another theory suggests it might be a white dwarf, the dead core of a sun-like star that somehow has enough leftover magnetic energy to flare at that rhythm. A handful of researchers have proposed it is a binary system where two compact objects orbit each other every 18 minutes, generating radio emission at the moment of closest approach. None of these explanations fit cleanly. Since GPM J1839-10 was announced, at least 3 more objects with similar slow, dead zone pulsing have been found. A whole new category of cosmic oddity has opened up, and nobody yet owns a theory that contains it. To find this signal, you have to go back further than any telescope can see, back before galaxies, before most of the stars you've ever heard of, back to a time when the universe was barely 180 million years old, still almost completely dark, with the first stars in the cosmos just beginning to switch on. Astronomers call that era the Cosmic Dawn. For decades it was considered permanently out of reach. The first stars were too faint, too far, too ancient to imagine catching their light directly. The only way to study them was going to be indirect, through the shadow they cast on the hydrogen gas that filled the young universe. In 2018, an experiment called EDGES, which stands for Experiment to Detect the Global Epoch of Reionization Signature, announced it had done exactly that. The team had set up a small radio antenna in the Australian outback, far from any city, shielded from interference, and pointed it straight up at the sky. They listened patiently for a very particular tone. A faint dip in the background of radio noise at a frequency of 78 MHz, the exact echo you would expect if the first stars had lit up the hydrogen gas around them and temporarily changed the way that gas absorbed the universe's ambient radiation. They found the dip. It was there, weak but measurable, exactly where theory said it should be. That was the first miracle. Then came the problem. The dip was more than twice as deep as any model had predicted. Standard cosmology had no explanation for why the early hydrogen gas would have been that cold. Some extra mechanism had to be cooling the primordial gas further than any known physics allowed. The implications were massive. One possible explanation involves dark matter interacting weakly with ordinary hydrogen and drawing heat away from it, which would be the first direct evidence ever recorded of dark matter behavior. Another possibility involves a bath of extra background radiation from some unknown source in the early universe. A third, more disturbing option is that something is simply wrong with our models of how the early cosmos evolved. The result was so strange that the global community demanded confirmation. A separate team in India built a competing experiment called CERAS-3, a radio antenna mounted on a floating raft in a lake to minimize interference. In 2022, CERAS-3 published its results. They saw no signal at all where EDGES claimed one existed. That contradiction has not been resolved. Both teams stand by their data. Both instruments were engineered with different kinds of error minimization. One of them is measuring something the other is missing, or one of them is being fooled by local interference in a way nobody has yet diagnosed. The ancient whisper, if it is real, carries information about the very first generation of stars ever to exist. Those stars are long dead, burned out within a few million years of their birth, leaving behind only their shadow in the cosmic background. If Edges is correct, then dark matter may be doing something our current theories never predicted. If Ceres 3 is correct, then the earliest period of star formation remains almost entirely beyond our reach. The signal waits. The universe's first light may still be speaking if anyone can tune in properly. In the summer of 1997, a network of underwater microphones stationed across the Pacific Ocean recorded a sound so loud that it was picked up by sensors more than 3,000 miles apart. 3,000 miles. The sensors had been built during the Cold War by the United States Navy, originally to track Soviet submarines, and had been reopened for civilian science in the early 1990s. They were among the most sensitive listening devices ever deployed on Earth. Whatever made the sound had to be enormous, louder than any animal ever recorded, louder than the loudest blue whale by a factor of several times over, louder than an industrial ship engine, loud enough to travel through thousands of miles of seawater and still register on hydrophones on the other side of the ocean. Scientists at the National Oceanic and Atmospheric Administration listened to the recording. It rose in pitch over about a minute, from a deep rumble into a higher moan before fading out. They called it the Bloop, and they had no idea what had made it. The frequency profile was unusual. Some animal sounds have characteristic patterns. Whales moan in slow, long calls. Dolphins click in fast, short bursts. Fish grunt and drum. The Bloop had the variability of an animal vocalization, the pitch rising and falling as if something living was producing it. Yet the raw volume was beyond anything biology seemed capable of. For years, the mystery fed a quiet panic in the online corners of the internet. Conspiracy blogs filled with theories about ancient sea creatures. Fiction writers borrowed the name for their own stories. The fact that the sound came from a region of the South Pacific, roughly near the location of a famous fictional underwater city in old horror stories, did not help calm the speculation. Scientists kept working. They mapped where the Bloop had come from. They listened for more. Occasionally similar sounds would appear in the data, strong rising moans in the same general region of ocean. Each one would provoke a new round of public curiosity before fading again. In 2005, researchers with NOAA began comparing the acoustic signature of the Bloop with another kind of sound they had been cataloguing for years: ice quakes. Massive cracks forming in Antarctic ice shelves as pieces broke off and ground against the bedrock below. When a huge slab of glacial ice fractures and scrapes across the seafloor, it generates exactly the kind of long rising moan that the Bloop displayed. By 2012, the connection was considered solid. The Bloop, and several similar sounds from the same region, were matched to the carving of icebergs in the Antarctic. As the planet warmed, more ice was breaking off the continent, and the cracking was echoing through the ocean with enough power to travel across hemispheres. The explanation was rational, well supported, and deeply unsatisfying to the public. The mystery had been explained, but its replacement was also unsettling. Climate change, in other words, had grown loud enough to be heard underwater from one side of the planet to the other. The oceans carry other unexplained sounds too. The Bloop may have been solved. The rest of the catalogue, as the next chapter will show, has not been so lucky. Of all the strange sounds recorded by the same underwater microphones that caught the Bloop, One stood out for a reason that had nothing to do with volume or drama. The upsweep was not the loudest signal in the archive. It was not the most violent. It was simply the most persistent. Something in the Pacific Ocean had been making it, quietly and continuously for decades. The Navy's underwater listening network first picked up the sound in 1991, when researchers began going through older tapes and fresh recordings. The signal consisted of a series of narrow tones that climbed slowly in pitch, each one sweeping upward like a submerged whistle. It repeated over and over, sometimes faster, sometimes slower, sometimes louder in the summer months, sometimes quieter in the winter, but always there. Unlike the bloop, the upsweep did not come and go in rare, dramatic bursts. It was more like the hum of a distant factory that nobody could find. Month after month, year after year. When scientists triangulated its origin, they traced it to a remote region of the Pacific Ocean, roughly halfway between New Zealand and South America. A stretch of deep sea so empty and so far from human activity that nothing obvious should have been producing any sound at all. The hunt for its source has been ongoing ever since. Early suspects included undiscovered whale species, since large cetaceans produce long-rising calls at similar frequencies. But no whale has ever been observed making a sound of this duration or of this remarkable consistency for decades on end. The call would have to be coming from the same individual for longer than any known whale has ever lived. Another suspect was volcanic activity. The region near the source includes a chain of underwater volcanoes. When magma meets seawater, it can boil, crack, and fracture rock, producing long, sweeping tones that bear some resemblance to the upsweep's pattern. This theory has gained ground over the years. Many researchers now believe the signal is produced by hydrothermal vents, where superheated water from inside the Earth forces its way up through narrow rock chimneys on the seafloor. The moving water, combined with boiling dissolved gases, could create the repeating whistle effect captured by the microphones. Here is the catch. No specific vent or volcano has ever been confirmed as the source. The triangulation points to a wide area of seafloor that has never been surveyed in detail. Deploying submersibles to the deep Pacific is expensive, slow, and politically complicated. No expedition has yet gone to the exact location to listen from underneath. The upsweep has also been weakening over the past 2 decades. Its intensity has dropped, and the individual tones have become fainter on the hydrophones. If the volcanic theory is right, whatever underwater process is producing the sound may be winding down. A vent system might be cooling. A magma chamber might be settling. The signal could fade out entirely within our lifetimes, leaving behind only the recordings. Or it could be something no hydrothermal theory has properly explained. An unknown biological source, an unresolved sediment process, a slow geological rhythm that nobody has mapped. The ocean holds onto its secrets well. The next strange sound we will examine did something the upsweep never did. It left the water entirely. In the small high desert town of Taos, New Mexico, residents have been reporting the same maddening complaint for more than 30 years. A low, steady humming sound, heard most clearly at night, rumbling at the edge of audibility. Those who hear it describe it as a distant diesel truck idling, or a far-off washing machine that never finishes its cycle. It is loud enough to ruin sleep, loud enough to cause headaches, loud enough that in 1993, residents demanded a formal investigation, and yet no microphone has ever reliably recorded it. The investigation was a serious one. Congress directed scientists from several universities, including Los Alamos National Laboratory, the University of New Mexico, and Sandia National Labs to deploy sensitive acoustic monitoring equipment around the affected areas. Teams set up microphones in the homes of people who heard the hum most strongly. They set up broader microphone arrays across the town to triangulate any potential source. They ran equipment for weeks at a time, covering every frequency from the deepest subsonic rumbles to the highest audible tones. The microphones captured ordinary background noise, cars passing, wind moving across sagebrush, the occasional airplane overhead. Nothing that matched the hum that residents described. The sound, if it existed outside of people's heads, was too weak to register on equipment that could pick up footsteps from a quarter-mile away. But the people hearing it are not making it up. Only about 2% of the town's population perceives the hum. Those who do consistently agree on its qualities. A low-frequency drone, a rhythmic throbbing, heard more clearly indoors than outdoors, worse in the middle of the night than during the day. 2% is small, but it is not nothing. In a town of several thousand, that adds up to dozens of people reporting identical symptoms without any obvious way to have coordinated their stories. The Taos case is not unique. Similar hums have been reported in Bristol, England since the 1970s, in Windsor, Ontario since around 2011, in Kokomo, Indiana in the early 2000s. In each case, a minority of residents describes a persistent low-frequency sound, while microphones register nothing unusual, and the majority of neighbours hear only silence. Theories about the cause break into roughly two camps. The first believes the hum is a real environmental phenomenon that current microphones cannot detect well, perhaps very low-frequency vibrations transmitted through the ground rather than the air. Industrial equipment, military installations, deep underground processes, or large-scale traffic could in theory produce such vibrations. The Windsor hum was eventually traced to a steel mill operating across the river in Michigan. The Kokomo hum was linked to specific factory machinery. The Taos investigation found no such local source. The desert around the town is largely empty. There are no heavy industries nearby. Military installations exist, but at distances that would normally rule them out. The second camp suggests the hum arises inside the listeners themselves, a phenomenon of the inner ear, the auditory nerves, or the brain's own processing. Spontaneous tones generated by neurons without any external source. Supporting this view is the fact that many hum hearers develop the perception gradually, often in middle age, a pattern that aligns with the onset of certain auditory conditions. Neither camp has produced a definitive answer. Somewhere in Taos tonight, dozens of people lie awake, listening to something no instrument can find. Throughout the 1970s and 1980s, ham radio operators and commercial broadcasters all over the world shared one persistent annoyance. A sharp, rhythmic tapping sound that would suddenly sweep across their shortwave frequencies, drowning out everything else in its path. 10 taps per second, strong enough to punch through from thousands of miles away, wide enough to blanket huge swathes of the radio spectrum. People called it the Russian Woodpecker. The name stuck because the sound really did resemble a mechanical woodpecker knocking on wood, and because the signal was clearly coming from somewhere inside the Soviet Union. Pinpointing the exact source took years of triangulation work from Western listeners, but eventually it became clear that the transmissions were originating from a facility in northern Ukraine, near a city most of the world would not hear of until disaster struck: Chernobyl. The Soviets refused to acknowledge the signal. Western intelligence agencies suspected it was a military transmitter of some kind, but nobody had firm evidence. Theories ran wild. Some people believed the Woodpecker was a mind control weapon, a long-range broadcast designed to manipulate the brainwaves of enemy populations. Others thought it was a weather control experiment, an attempt to alter atmospheric patterns through electromagnetic bombardment. A few believed it was simply a communications jammer designed to disrupt NATO operations. The truth, when it finally emerged after the fall of the Soviet Union, was far more practical and, in its own way, more unsettling. The signal was coming from a massive facility called Duga, which translates as arc. It was part of an over-the-horizon radar system, designed to detect incoming intercontinental ballistic missiles the moment they were launched from the United States. By bouncing radio waves off the ionosphere, the radar could see over the curvature of the Earth, providing a few extra minutes of warning before a nuclear strike. The physical structure of Duga was monumental. A lattice of steel towers nearly half a mile long and about 460 feet tall. Even today, long after the facility was abandoned, the towers still stand inside the Chernobyl exclusion zone, rusting slowly, visible for miles in every direction. Photographs from urban explorers who have snuck inside show a cathedral of wires and antennas, dwarfing anything built for Western radar systems of the same era. The timing of the Woodpecker's shutdown is where the story bends strange again. The signal went silent in the months following the Chernobyl nuclear disaster in 1986. Officially, the facility was decommissioned because advances in satellite technology had made over-the-horizon radar less necessary. A handful of Ukrainian researchers have proposed a different theory. They suggest that the Duga facility was operating on such high power that the surrounding electrical grid had been pushed to dangerous limits for years, and that electrical anomalies in the region may have contributed to the reactor failure at Chernobyl. This theory remains controversial, without strong supporting evidence. The Russian Woodpecker itself has been explained. Its purpose, its location, and its engineering are no longer secret. Yet the site has become something else in the decades since it went quiet. A rusting monument in a forbidden zone, built to listen for an apocalypse that never came, standing a few miles from an apocalypse that did. The next chapter moves to a Russian signal that has never gone silent, and it is still broadcasting right now. Tune a shortwave radio to a frequency of 4,625 kHz right now, at this moment. You will hear a sound that has been playing almost without interruption for more than 40 years. A short monotonous buzz about 1 second long, repeating roughly 25 times per minute from a transmitter somewhere deep inside Russia. The station has no official name. Hobbyists call it UVB-76, or simply the Buzzer. It began broadcasting in the mid-1970s. No government has ever formally claimed it. No public announcement has ever explained its purpose. Yet the signal has continued through the collapse of the Soviet Union, through decades of political turmoil, through the end of the Cold War and whatever came after. The buzz has outlasted the country that built it. For most of that time, the broadcasters consisted of nothing but the endless buzz. Occasionally, however, the buzzing stops, and when it stops, a voice comes on. The voice speaks in Russian. It reads strings of letters and numbers in a flat, formal tone. A typical message might go something like this: the station identifier, followed by a code phrase, followed by a long sequence of digits and names. The messages are brief, usually under 30 seconds. When the voice finishes, the buzzing resumes as if nothing happened. These voice broadcasts are rare. For years at a time, only the buzz plays. Then, without warning, a burst of messages will come through. In the 1990s, there were maybe 1 or 2 voice messages per year. Since about 2010, the frequency has increased. Now, shortwave listeners log several voice transmissions per month, sometimes more. The content of the messages is almost impossible to interpret from outside. Ham radio communities have assembled databases of every recorded transmission going back decades. Patterns emerge. Certain phrases repeat. The code words rotate, suggesting a simple rotating cipher. Some analysts believe the messages are routine status checks for a military communication network, a kind of electronic roll call confirming that Russian strategic forces are operational and in contact. Others have proposed a more disturbing theory. The buzzer may be part of the Russian dead hand system, a semi-automated nuclear retaliation protocol designed to launch missiles if the country's leadership is wiped out in a first strike. In this theory, the constant buzzing serves as a heartbeat. As long as the buzz continues, the system knows that command and control is intact. If the buzz ever stopped without authorization, it would signal that something catastrophic had happened, potentially triggering automated weapons launches. There is no confirmed evidence for the dead hand interpretation. The Russian government has never discussed the station publicly. Former Soviet military personnel have made vague comments over the years, sometimes suggesting a military role, sometimes refusing to speak at all. In 2010, something strange happened at UVB-76. The buzzing stopped for several hours. During the silence, a series of unusual sounds came through. Muffled voices, banging noises as if furniture was being moved, a dog barking in the background. Then the buzz resumed. Whatever the station really is, somebody is tending to it. A room exists. A transmitter exists. The buzz continues tonight. At this very moment, a hum from a country that half the world considers an enemy, broadcasting a rhythm nobody outside the facility is allowed to understand. UVB-76 is not alone. It is one member of a much stranger, much older community of mysterious broadcasts that have been rolling across the world's shortwave frequencies since at least the 1920s. Listeners call them numbers stations, and many of them are still active today, transmitting coded voices from hidden locations across every populated continent on Earth. A typical numbers station broadcast follows a chilling pattern. It begins with an identifying melody, sometimes a few bars of folk music, sometimes a handful of synthesized tones. This is the station's signature, the equivalent of a phone ringing before the call connects. Then a human voice, often female, sometimes a child, sometimes a mechanical synthesis, begins reading long sequences of numbers or letters in a steady, emotionless tone. 5-digit groups, 10-digit groups, 100 of them in a row. The voice never hurries, never stumbles. Then the melody plays again, and the transmission ends. The first confirmed numbers stations went on the air during the early years of radio itself. By the 1950s, they had exploded in number. American, British, Soviet, Czech, Cuban, Chinese, Israeli and North Korean stations have all been identified by enthusiasts over the decades. A few of the more famous ones earned nicknames: the Lincolnshire Poacher, Magnetic Fields, Yosemite Sam, the Cherry Ripe. Each one had a distinctive opening melody that allowed listeners to identify the broadcaster instantly. The purpose of numbers stations is an open secret. Almost all of them are used by intelligence agencies to send messages to spies operating inside foreign countries. Shortwave radio can travel thousands of miles by bouncing off the ionosphere. A spy with a cheap radio and a one-time pad codebook can pick up a broadcast from anywhere in the world and decode the message using the pad. Because the codebook is truly random and used only once, the messages are mathematically unbreakable, without access to the original pad. This is why number stations have survived into the modern era. Email can be traced, phones can be tapped, satellite links leave records. A shortwave broadcast goes out in every direction at once. Anyone listening could be the intended recipient. The government transmitting has no way of knowing where in the world the spy is actually sitting, which makes catching them almost impossible. Some stations have famously odd behaviors that remain unexplained. Yosemite Sam, an American station active in the mid-2000s, opened every broadcast with a 10-second clip of the cartoon character Yosemite Sam shouting at cowboys, followed by a burst of digital data. The station has since gone silent. Nobody has explained why the intelligence service chose a cartoon voice. The Czech station called Sputnik used to transmit different melodies depending on which spy network the message was intended for. Israeli stations have reportedly been used to trigger sleeper agents in surrounding countries during times of crisis. At least 20 number stations are believed to be operating at any given moment, somewhere on the shortwave bands. If you have a decent radio and patience, you can tune in tonight. Somewhere in the noise, a voice will be reading numbers. You will not know which country it comes from, or who it is addressed to, or what the numbers mean. Only that somewhere on Earth, someone else is listening for that exact sequence, ready to receive their orders. The next chapter returns to the stars, and to a modern attempt to hear ghosts from the past. In 2020, a radio astronomer named Robert Gray died. He had spent more than 20 years of his personal time and personal money pointing telescopes at the same patch of sky that produced the original WOW signal of 1977. He listened for hundreds of hours. He coordinated time on dishes in Illinois, Australia, and West Virginia. He never heard the signal repeat. He went to his grave hoping someone else would keep listening. Someone did. A small international team picked up his work after his death and launched a project called WOW at Home. The premise was simple: use modern radio telescopes, more sensitive than anything available in 1977, and scan the original WOW coordinate repeatedly over months and years, looking for any hint of a return transmission. The effort received a quiet boost in 2022, when a telescope in Puerto Rico's successor site began dedicating observation windows specifically to the WOW region. The equipment used today is thousands of times more sensitive than the Big Ear telescope Jerry Eman worked with. If the original signal had repeated at even a fraction of its previous strength, the new telescopes would have caught it instantly. Nothing. Years of observations, hundreds of hours of integrated listening time, silence. Then, in early 2024, something unusual happened. A Spanish astronomer named Alberto Caballero, working with limited equipment in his backyard, started analyzing archive data from a different telescope that had scanned the WOW region in the 1990s. He found something nobody had flagged before: a faint, narrow radio source, not as strong as the original WOW signal, but sitting in almost exactly the same patch of sky. Caballero published his finding. The astronomy community responded with cautious interest. The signal he had identified was much weaker than the original, which made it hard to distinguish from background noise with certainty. But its position was strikingly close to where the 1977 burst had originated, and it did not match any known star, galaxy, or satellite. He proposed a candidate source, a sun-like star called 2M ASS 1928-19824, located about 1800 light-years from Earth, which happened to sit close to the edge of the original WOW coordinate range. The star is roughly similar to our Sun in temperature and age. If a civilization exists somewhere nearby, transmitting a signal aimed in our direction would take about 1800 years to reach us. Something broadcast around the time of the fall of the Roman Empire would be hitting our antennas roughly now. The claim remains speculative. Follow-up observations have not confirmed a clean second detection at that star. But the hunt has intensified. Several teams have now added that star system to their priority target lists for the next decade of SETI work. A more ambitious project called the Breakthrough Listen Initiative, funded with $100 million over 10 years, has scanned hundreds of thousands of stars across our galaxy, searching for narrow band transmissions that do not match any known natural source. As of 2025, the project has flagged more than 1 million potentially interesting signals. Almost all have been ruled out as satellite interference, terrestrial radio leakage, or instrumental noise. A small handful remain unexplained. None of those unexplained candidates sits anywhere close to the original WOW coordinate, which means either the signal was a one-time anomaly, or whoever sent it chose not to repeat it, or the answer is hiding in data nobody has looked at yet. Whoever was whispering in 1977 has gone very, very quiet. Not every signal that looks artificial actually is. Sometimes the universe fakes us out, producing radio patterns so clean and so structured that scientists initially mistake them for something engineered. The class of objects most responsible for this illusion has a name that sounds like science fiction: Magnetars. A magnetar is a type of neutron star, the leftover core of a massive star that exploded as a supernova. Neutron stars are already exotic. They pack the mass of our Sun into a sphere about 12 miles across, so dense that a teaspoon of their material would weigh about 1 billion tons on Earth. Their gravity is intense enough to bend light noticeably. They spin, some of them hundreds of times per second, beaming radiation across the cosmos like frantic cosmic lighthouses. Magnetars are the extreme end of this family. Their magnetic fields are roughly 1,000 trillion times stronger than Earth's. If a magnetar approached within 100,000 miles of Earth, its magnetic field would rip apart every electronic device on the planet and scramble the atomic structure of every living thing. No spacesuit, no shielding, no distance under a light year could protect a human from one. Magnetars are also volatile. They build up enormous stresses in their crusts as their magnetic fields twist and slip. When something snaps, the release of energy is catastrophic. A single flare can outshine the entire galaxy it lives in, briefly, in gamma rays. Smaller flares produce intense bursts of radio energy. Here is where the confusion starts. In April of 2020, a magnetar in our own galaxy called SGR 1935+2154 produced a radio flare that, for the first time, closely resembled the fast radio bursts astronomers had been tracking from distant galaxies. The burst was shorter than a blink, intense enough to be detected easily, and it came from a known object that scientists could continue to monitor. This was a breakthrough. For years, the leading theory for fast radio bursts had pointed at magnetars as the likely source, but no direct link had ever been confirmed. The 2020 event locked in the connection. At least some fast radio bursts, the ones we've been worrying might be alien, were magnetars doing what magnetars do. That conclusion came with a complication. Magnetars do not explain everything. The bursts they produce are generally not as bright as the most extreme cosmic fast radio bursts on record. They do not match the precise repeating patterns seen in signals like FRB 12102, and they definitely cannot account for the clock-like rhythm of some repeating sources which arrive with the regularity of a metronome. Furthermore, magnetar flares occasionally mimic artificial signals in more unsettling ways. A flare with certain polarization and frequency characteristics can look, for a few seconds, like a deliberately engineered narrow-band transmission. SETI researchers have been fooled more than once. Each time, deeper analysis reveals the natural source. But the confusion is not trivial. A large magnetar flare seen from the edge of the universe could in principle show properties that look disturbingly intentional. What makes this uncomfortable is the inversion it forces on us. If natural objects in our galaxy can produce signals that briefly look artificial, how confident can we ever be when a similar signal comes from somewhere we cannot visit? The line between natural and engineered grows blurrier every year, and that blur gets worse with the object in the next chapter. In the summer of 1967, a 24-year-old graduate student at Cambridge University in England was scrolling through hundreds of feet of paper chart recordings produced by a new radio telescope she had helped build. Her name was Jocelyn Bell. She was tired. The telescope generated about 100 feet of chart paper every day, and she was responsible for analysing all of it by hand. In the middle of one of those charts, she spotted something odd. A small, scrappy signal, about a quarter-inch wide, showing up in a part of the sky she'd already scanned. Most sources she saw were either long, slow drifts from quasars or short, sharp spikes from terrestrial interference. This signal was neither. It was too fast for a quasar, too clean for interference. She flagged it to her supervisor, Anthony Hewish. He initially dismissed it as noise. She pushed back. She asked for permission to re-observe that part of the sky when the telescope next swept over it. He agreed reluctantly. On November 28, 1967, she pointed the telescope back at the coordinate and recorded the signal again. This time she caught it in high time resolution. The signal was a pulse, a short, sharp burst of radio energy, repeating every 1.33 seconds with the accuracy of an atomic clock. The regularity was astonishing. Nothing natural in the universe was supposed to produce a signal that orderly. Radio bursts from space were known to be chaotic, varying in timing and intensity. This object was ticking with metronome precision. Bell and Hewish were quietly worried. They had no theoretical explanation. The signal's timing was so consistent that it looked like a broadcast from an intelligent civilization. For a few weeks, they seriously entertained that possibility. Half as a joke, half as a real hypothesis, they labelled the source LGM-1. LGM stood for Little Green Men. Bell kept working through her chart data. About 6 weeks after the first detection, she found a second pulsing source in a completely different part of the sky. Different period. Same metronome regularity. The team realized the truth. Two civilizations in two random directions of space, both broadcasting with perfect timing, was statistically absurd. Whatever these objects were, they had to be natural. The actual answer took about a year to confirm. These were neutron stars, the same compact remnants discussed earlier, but spinning extraordinarily fast and beaming a narrow cone of radio waves out of their magnetic poles. As the star spun, the beam swept across space like a cosmic lighthouse. Each time the beam pointed at Earth, the telescope caught a pulse. The timing was clock-like because it was literally a rotation period. The spin of a city-sized dead star cranked to the speeds of an industrial turbine. Jocelyn Bell's discovery launched an entire field of astronomy. Thousands of pulsars have now been catalogued. They're used as precision clocks to test general relativity, hunt gravitational waves, and map the Milky Way's magnetic field. In 1974, the Nobel Prize in Physics was awarded for the discovery of pulsars. Anthony Hewish received it, along with a colleague. Jocelyn Bell did not. The decision was widely criticised at the time and remains one of the most famous omissions in the history of the Nobel Committee. Bell has spoken gracefully about it for decades. She was the one who almost convinced the world that aliens had been found. Return for a moment to Tabby's star, the object whose irregular dimming briefly made half the internet believe we had discovered an alien megastructure. The mainstream explanation now says the dimming is caused by uneven clouds of dust orbiting the star. Case closed, according to most astronomers, and yet a stubborn minority of researchers refuses to fully let the megastructure idea die. The concept behind it comes from a British mathematician named Freeman Dyson, who in 1960 published a short paper proposing that any sufficiently advanced civilization would eventually run out of energy on its home planet. To keep expanding, such a civilization might build enormous structures around its home star to harvest stellar energy directly. A full shell would be mechanically impossible, but a swarm of individual collectors spread across a star's orbit would be plausible, at least in principle. This became known as a Dyson swarm. The idea was largely theoretical, tossed around in science fiction, until someone realized that such a swarm would produce a very specific signature in the light curve of the star it surrounded. The star would dim in irregular asymmetric ways by large percentages over long time periods as the artificial objects transited across it. The signature would look, in other words, uncannily like what Tabby's star was showing. Jason Wright's 2015 paper on the alien megastructure hypothesis was partly a technical paper, partly a provocation. He argued that while natural explanations were more likely, astronomers had a professional obligation to at least consider the artificial possibility and rule it out systematically before dismissing it. His paper sparked a decade of follow-up work. Here is where the debate stands today. Most astronomers believe the dust cloud model accounts for the Tabby's star dimming, but the specific shape of that dust cloud remains difficult to model precisely. The dips in brightness do not fit any single, clean orbital configuration. Some researchers have noted that the observed dimming patterns show subtle features that dust alone does not easily reproduce. More significantly, a small number of other stars have since been identified with similar dimming behavior, not as dramatic as Tabby's star, but puzzling in similar ways. Each one has been found to have its own quirks, its own partial explanations, its own unresolved questions. The search for true Dyson swarm candidates has continued quietly. In 2024, a team searching through infrared surveys identified 7 stars with unusual heat signatures that could, in theory, match what a partial Dyson swarm would produce. A Dyson swarm absorbs visible light and re-emits the energy as infrared heat. Stars with excess infrared glow, without obvious dust explanations, are exactly the kind of targets this theory predicts. The 7 candidates are all relatively nearby, within a few hundred light years. Each one is under follow-up observation. Early results suggest that most can probably be explained by circumstellar dust from ordinary astrophysical processes. At least 2 remain unexplained, with no confirmed dust source and spectra that do not cleanly match any known stellar phenomenon. This is not evidence for alien megastructures, it is a list of stars that nobody has been able to fully explain yet. The modern scientific consensus holds that natural phenomena are vastly more likely than alien engineering in every case, and that consensus is almost certainly correct. But the method of searching, looking for stars that behave wrongly, and examining them individually, has quietly become part of mainstream astronomy. Tabby's star pulled the idea out of the shadows and made it legitimate. The cosmic microwave background is the afterglow of the Big Bang itself. It is the oldest light in the universe, emitted when the cosmos was about 380,000 years old and had finally cooled enough for atoms to form. Before that moment, light could not travel freely through space. After it, a flash of radiation flooded the universe, and that flash has been expanding and cooling for 13.5 billion years ever since. Today it arrives at Earth as a faint glow of microwaves, detectable from every direction in the sky. For decades, astronomers have mapped this background in exquisite detail. The light is almost perfectly uniform, varying by only tiny amounts across different parts of the sky. These tiny variations carry the fingerprints of the early universe, the seeds that eventually grew into galaxies and clusters and everything we see. But hidden in the patterns of that light, something strange has been found. In 2004, a team analysing data from NASA's WMAP satellite noticed that certain large-scale features in the cosmic background were not random. They seemed to line up with each other in ways that should not happen by chance. Specifically, the hottest and coldest regions on the largest measurable scales appear to share a preferred direction, as if the universe had an invisible axis that governed their alignment. The discovery became known as the Axis of Evil, a deliberately provocative name chosen by the researchers to highlight how much the finding threatened standard cosmology. The standard model of the universe assumes that on the largest scales space has no preferred direction. Every direction should be statistically identical to every other. The Axis of Evil suggested otherwise. Follow-up observations by the Planck satellite in the 2010s confirmed that the alignment was not a quirk of the WMAP instrument. It was really there in the data. And worse, the preferred direction seemed to point suspiciously close to the plane of our own solar system, raising the possibility that our local environment was somehow contaminating our measurements of the universe itself. A contamination explanation would actually be reassuring. If the effect came from dust in our own solar system, or from how our telescopes oriented themselves, it would not threaten cosmology. Unfortunately, the contamination explanations have not held up well. The alignment persists even after careful subtraction of known local effects. Several theoretical possibilities remain on the table. One suggests that the early universe may have had a preferred direction that standard inflation models cannot explain. Another proposes that the cosmos is not infinite but has a specific finite shape, with dimensions that would produce such an axis. A third, more exotic hypothesis suggests that the observable universe is embedded in a larger multiverse, and that the axis we see reflects the orientation of other cosmic bubbles beyond our own. None of these ideas has strong supporting evidence. The axis remains, for now, an anomaly in the data that the standard model cannot comfortably absorb. What makes the finding so unsettling is that the cosmic microwave background is supposed to be the cleanest, most universal, most democratic signal in the universe. It was produced everywhere, in every direction, at the same instant. Finding structure in it is like finding handwriting in an empty sheet of paper. The universe should not have a preferred direction, and yet, faintly, it seems to. The next chapter examines something even more troubling in that same background light. Buried inside the cosmic microwave background, in a particular direction of the southern sky, There is a region where the universe appears to have less light than it should, about 1.5 billion light-years across, colder than the surrounding microwave glow by a small but measurable amount, larger than any structure predicted by standard cosmology. Astronomers call it the cold spot. The cold spot was first identified in the early 2000s in WMAP data, and its existence was confirmed by higher resolution observations from the Planck mission a decade later. Its reality is not in question. What is in question is what it represents and why it exists. In a normal cosmological model, the early universe should have had small random fluctuations in temperature. Some regions slightly hotter, some slightly colder, with an overall distribution that follows predictable statistical patterns. The cold spot breaks those patterns. It is too big. It is too cold. It sits too far from the statistical tail that cosmology comfortably expects. The odds of such a feature arising by chance are estimated at less than 1 in 1,000. A possible explanation involves what cosmologists call a supervoid. If a truly enormous region of relatively empty space sits between us and the cosmic background in that direction, the light passing through it would lose a small amount of energy due to the expansion of the universe. This effect, called the integrated Sachs-Wolf effect, would make that region appear slightly cooler than its surroundings. Evidence for such a supervoid was published in 2015. A team of astronomers mapping the distribution of galaxies in the direction of the cold spot reported finding a region about 1.8 billion light-years across, with significantly fewer galaxies than expected. The findings seemed to resolve the mystery. The cold spot was the shadow of a giant empty region of space. Then the problem came back. More detailed follow-up studies found that the proposed supervoid, even if real, was not empty enough to account for the full temperature deficit observed in the cold spot. The void could explain maybe 1/10 of the effect, at most. Something else was making the region colder than it should be. The supervoid explanation, while partially supported, was insufficient. The remaining explanations grow increasingly strange. One possibility is that the cold spot represents a rare statistical fluke, a 1 in 1,000 random occurrence that happened to land exactly where we can see it. The universe is vast and unlikely features eventually appear somewhere. A more intriguing hypothesis involves what theorists call a cosmic bruise. According to certain versions of the multiverse theory, our universe may have collided with another universe in the distant past. Such a collision would leave a circular imprint on the cosmic background, a region where the light is distorted from the impact. Some researchers believe the cold spot could be evidence of exactly that. If so, we would be looking at the direct scar of a collision between our cosmos and another reality. This idea has almost no supporting evidence, and most cosmologists consider it too speculative to take seriously. But the cold spot continues to defy simpler explanations. Every attempt to dismiss it statistically has run into trouble. Every attempt to attribute it to known physics has come up short. A bruise on the sky marking a possible collision with another universe. That is still technically on the table. Somewhere in the universe right now, a neutron star may be moments away from collapsing into a black hole. When it does, it will produce one of the briefest and most powerful events physics can describe. A single millisecond burst of radio energy, so intense that astronomers on the other side of the cosmos could detect it, followed by eternal silence as the new black hole swallows everything that remains. The theoretical name for this event is a Blitzer. The concept was proposed in 2013 by a team of Dutch and German theorists, trying to explain the origin of fast radio bursts. The idea worked like this. A neutron star under normal conditions supports itself against collapse through a combination of internal pressure and rotation. A slowly spinning neutron star above a certain mass threshold, about 2.5 times the mass of our Sun, should immediately collapse into a black hole. But a rapidly spinning one can temporarily support itself through the outward push of its own rotation, even at masses where gravity would otherwise win. These are called supramassive neutron stars. They are metastable. They look like normal neutron stars from the outside, but they are secretly doomed. Over millions of years, their rotation slows as they radiate energy away through their magnetic fields. At some point, the rotation drops below the critical threshold. Support collapses. Gravity takes over in a fraction of a second. As the star crushes inward, its magnetic field, formerly locked to the rotating crust, snaps free and briefly unleashes its full stored energy. That energy escapes as a burst of coherent radio emission before the newly formed black hole's event horizon closes around it. The burst lasts perhaps 1,000th of a second. It is extraordinarily bright, and then the source is gone forever, swallowed by the black hole it created. No blitzer has ever been definitively observed, but the idea fits certain classes of non-repeating fast radio bursts uncomfortably well. A single bright burst from a single location in deep space, never seen to repeat, never associated with any known host object, coming from what appears to be an otherwise unremarkable patch of a distant galaxy. That is exactly what a blitzer should look like. The implication is grim. If blitzers are real, then every non-repeating fast radio burst we catch is a death announcement. Somewhere in the universe, a massive neutron star has just given up the fight against its own gravity, collapsed into a black hole, and sent us its final transmission before disappearing. Estimates suggest that blitzer events should be rare but not vanishingly so. Perhaps a handful per century per galaxy, across the billions of galaxies in the observable universe. This works out to thousands of them happening every day somewhere in the cosmos. Most would be too distant to detect. A few would be close enough to register on our most sensitive instruments. The hunt for confirmed blitzer signals is active. Surveys like CHIME, a radio telescope in Canada, have catalogued thousands of fast radio bursts. Machine learning algorithms sort them into repeating and non-repeating categories. The non-repeating ones are the blitzer candidates. Each one may represent the last moment of a star that had been slowly losing its battle with gravity for millions of years. Listen to any non-repeating fast radio burst with that in mind. Somewhere across the universe, something just died in front of you. The repeaters, though, tell a different story. Repeating fast radio bursts are rare. Out of thousands catalogued, only a small fraction have ever been confirmed to repeat from the same location. Among those repeaters, one source has captured particular attention because of a property that no theorist saw coming. It arrives on a schedule. The source is called FRB 1809-16.J 0158 plus 65. Astronomers who work on it just call it 180916. The signal comes from a spiral galaxy roughly 500 million light-years from Earth, relatively close by cosmic standards. The galaxy itself is ordinary, a rotating disk of stars and gas not unlike the Milky Way. What is not ordinary is the rhythm of the signal. Researchers analysing data from the CHIME telescope in British Columbia found that 180916 does not emit bursts randomly. Instead, it follows a 16.33-day cycle. For about 5 days at a time it is active, producing clusters of bursts. Then for about 11 days it falls silent. Then the active window opens again. This pattern is impossibly clean for a random astrophysical source. The cycle has been tracked for more than 5 years now. It does not drift. It does not decay. It keeps ticking like a cosmic clock. Explanations have proliferated. The leading theory suggests the source is a magnetar in a binary orbit around a massive companion star. As the magnetar orbits, it periodically enters regions where the companion star's stellar wind compresses its magnetosphere, triggering the bursts. This would explain the regularity as an orbital period, with the active window corresponding to the part of the orbit closest to the companion. The problem with this model is the specific duration of the active window. 5 days is a long time. An orbital mechanism should produce a sharper, shorter peak near closest approach. A 5-day flat plateau of burst activity is harder to get out of a simple binary system. An alternative theory proposes that the magnetar is undergoing precession, meaning its rotation axis is wobbling like a slowly tipping top. As the axis wobbles, its magnetic beam sweeps toward us during certain phases of the wobble and away during others. A 16-day precession cycle is extreme for any known neutron star. Most precess much faster or not noticeably at all. But it is not physically forbidden, and some exotic magnetar configurations could support it. A third possibility raises more troubling questions. The source could be something nobody has theorized yet. A compact object in a configuration that no standard model accommodates. New physics is a last resort in astronomy, invoked only when everything else has failed. For 180916, most researchers still believe conventional explanations will eventually prevail, but none has yet been confirmed. In 2022, astronomers pinpointed the exact location of the bursts within the host galaxy to within a few hundred light years. The bursts were coming from the outer regions of a spiral arm, a place where young stars form, but where the density of gas is relatively low. This environment fits poorly with some proposed models and fits awkwardly with others. The source itself, whatever it is, sits in a neighborhood that astronomers would not have predicted. Other repeaters with calendar-like rhythms have since been found. One has a 150-day cycle, another has a 60-day pattern. The universe, it turns out, keeps time in some corners we did not expect. In the years after the WOW signal was detected, a debate began within the SETI community that has never been fully resolved. Should we try to answer? The question is not academic. In 2012, to mark the 35th anniversary of the original detection, the National Geographic Channel partnered with the Arecibo Observatory to broadcast a reply toward the original coordinate. They collected roughly 10,000 messages from the public, compressed them into a single digital transmission, and pointed the giant Arecibo dish at the Sagittarius region. For about 3 hours, a signal left Earth on an outbound journey. Tweets, jokes, personal messages, scientific greetings, all aimed at a patch of sky that had whispered at us once and then gone silent forever. Many astronomers were furious. The reply had been sent without broad consultation within the scientific community. No international protocol had been followed. No careful consideration had been given to what a reply might actually mean. One radio astronomer publicly compared the decision to children screaming into a dark forest. This debate is older than the WOW signal itself. It is usually called the active SETI question, or the METI question, short for Messaging Extraterrestrial Intelligence. The classical SETI approach, developed by Frank Drake and others in the 1960s, is passive. We listen. If someone is out there, they are welcome to speak. We do not transmit deliberately because we do not know who is listening, and we cannot predict their response. METI proponents argue that this caution is outdated and cowardly. Humanity has been leaking radio and television signals into space for about a century already. Any civilization within 100 light-years has already received our broadcasts, whether we meant for them to or not. Deliberately transmitting a clearer, more organized message is therefore not a change in kind, only a change in clarity. The physicist Stephen Hawking took a famously different view. In multiple public statements before his death in 2018, he warned that humanity should actively avoid advertising its location. He argued that any civilization capable of receiving and responding to a message would likely be far more technologically advanced than us, and that first contact with a more advanced civilization has, throughout human history, tended to go very badly for the less advanced party. The comparison he drew was between European colonizers and the indigenous peoples of the Americas. Other scientists dismiss this concern as paranoia. They argue that the vast distances between stars make interstellar colonization effectively impossible, and that any advanced civilization would have its own motives and constraints that we cannot reasonably predict from earthbound examples. The scientific community has quietly adopted a kind of gentleman's agreement against coordinated active transmissions. There is no treaty, no enforcement mechanism, no law. Individual nations and projects could, in principle, send whatever they wanted at any time. Arecibo did it in 2012. Smaller projects have done it too. The WOW! Signal remains the only recorded event that might plausibly have been an attempt to contact us. If it was, the sender has not repeated. Perhaps because they lost interest. Perhaps because they moved. Perhaps because they concluded we were not worth speaking to again. Or perhaps because, after speaking once, they have been patiently waiting to see what we would do. For centuries, astronomers have known that something odd happens on Earth during total solar eclipses. Animals behave strangely. Cicadas fall silent. Birds stop singing. Cattle begin to lie down as if dusk has arrived. Wind patterns shift. Temperature drops, sometimes by more than 10 degrees Fahrenheit in a matter of minutes, as the moon's shadow passes over the landscape. But something else happens too. And this part is measurable by instruments, not just poetry. Radio signals on Earth change during an eclipse in ways that scientists have documented for decades, but still cannot fully explain. The ionosphere, the layer of the atmosphere about 50 to 600 miles above the surface, is responsible for most long-distance radio transmission on Earth. It gets ionized, meaning its atoms are stripped of electrons by ultraviolet light from the sun. When the sun's light is blocked during an eclipse, ionization drops briefly, and the ionosphere temporarily changes its properties. This much is well understood. What is less understood is how dramatically and unpredictably radio propagation responds to the change. During the August 2017 total eclipse across the United States, thousands of amateur radio operators participated in a coordinated experiment called the Solar Eclipse QSO Party. They recorded every contact they could make between stations in different states during the eclipse. The data revealed that radio signals in the medium and high-frequency bands behaved in complicated ways, with some paths opening up that normally do not work, and others becoming unusable for brief periods. More intriguingly, certain faint radio signals from space became detectable during eclipses that are nearly impossible to measure at other times. The ionosphere's dampening effect on incoming cosmic radio waves is normally strong enough to drown out the faintest signals. When the ionosphere thins during an eclipse, that dampening drops. For a few minutes, telescopes can hear fainter voices from the cosmos than they usually can. During the 2024 total eclipse across North America, several research teams organized observations of deep space objects through the ionospheric gap. A small team working with a radio array in New Mexico reported catching a faint narrow band signal that appeared in their data during totality and then vanished when the eclipse ended. The signal did not match any known satellite or terrestrial source. It was faint enough that normal sky conditions would have obscured it entirely. The team has been cautious about announcing anything. Their report noted that the signal could have come from distant radio interference that happened to align with the eclipse window or from a transient astrophysical event. Further follow-up during non-eclipse conditions has not reproduced the signal. What this means is that humanity's radio observations of space are always partial. The ionosphere above us acts like a dirty window. Most of the time, we can see through it well enough to do astronomy, but there is always a filter. Only during eclipses does the window briefly clean itself, and when it does, we sometimes hear things that should not be there. This has prompted a small but growing effort to coordinate radio observations during future eclipses. The 2026 total eclipse that will cross Iceland and Spain, the 2027 eclipse across North Africa, and the especially long 2033 eclipse in the Arctic are all being planned as research windows for this kind of work. If there is a faint signal out there that normally gets lost in the atmospheric hum, eclipses may be the only way to catch it. Each shadow of the moon is a brief invitation to listen more deeply. In 1977, the same year Jerry Eman circled the WOW signal, NASA launched 2 robotic spacecraft that would eventually travel farther than any human-made object in history, Voyager 1 and Voyager 2. Their mission was to explore the outer planets of our solar system, and after finishing that work, to keep going into interstellar space. Voyager 1 crossed what scientists call the heliopause in August of 2012, officially entering the vast empty region between the stars. Voyager 2 crossed it in November of 2018. Both spacecraft continue to function, powered by small nuclear generators that converted heat into electricity. Both kept sending back faint radio transmissions to Earth, across distances so vast that the speed of light itself became a noticeable delay in communication. As of 2026, Voyager 1 is about 15 billion miles from Earth. Signals from the spacecraft take more than 22 hours to reach us. The signals themselves are extraordinarily weak. Voyager's transmitter produces about 22 watts of radio power, roughly the output of a refrigerator light bulb. By the time that signal crosses 15 billion miles of space, it has weakened to a level that most radio telescopes could not detect at all. Only NASA's Deep Space Network, a series of massive dish antennas in California, Spain, and Australia, has the sensitivity required to pick up the signal at all. The whisper of Voyager has become a kind of ritual in the NASA community. Every few weeks, the Deep Space Network pauses its other tasks and listens for the spacecraft's faint carrier wave. The team uploads new instructions, downloads the small amount of data the spacecraft has gathered, and confirms that Voyager is still working, still flying, still sending. Problems have mounted in recent years. In late 2023, Voyager 1 began returning scrambled data. The spacecraft's flight computer was malfunctioning, producing streams of meaningless code instead of proper telemetry. For months, engineers at NASA worked to diagnose the issue remotely, with each transmission taking a full round-trip day to complete. They eventually traced the failure to a small chunk of memory in the computer that had become corrupted, possibly from cosmic ray damage accumulated over nearly 50 years in space. They rewrote the affected code, transmitted the fix, and waited. The spacecraft came back online in 2024. It resumed sending proper data. but the engineers know that every such recovery is borrowed time. The radioisotope generators on both Voyagers continue to lose power slowly, about 4 watts per year. Scientists estimate the spacecraft will run out of usable electricity sometime in the late 2020s or early 2030s. After that, the whisper will fall silent, but the spacecraft themselves will continue. Forever, effectively. There is nothing in interstellar space dense enough to slow them down on human timescales. Voyager 1 is headed in the general direction of a star called Gliese 445, which it will approach in about 40,000 years. Voyager 2 is headed toward Ross 248, which it will reach in a similar span of time. Each spacecraft carries a gold-plated record, the Voyager Golden Record, containing sounds and images from Earth. Greetings in dozens of languages, music from different cultures, whale songs, heartbeats. A message from Jimmy Carter, then the President of the United States. Long after the radios have fallen silent, the records will still be flying through the dark, waiting for someone to find them. In July of 2015, at a press conference in London, a Russian-Israeli billionaire named Yuri Milner announced the largest SETI project ever undertaken. $100 million, 10 years. Access to some of the best radio telescopes on Earth. A target list including 1 million nearby stars, the entire plane of the Milky Way galaxy, and 100 of the galaxies closest to our own. The initiative was called Breakthrough Listen. Stephen Hawking sat next to Milner at the press conference. Frank Drake, the founder of modern SETI, attended as well. The project carried the weight of decades of accumulated hopes. For most of its history, SETI had been chronically underfunded, relying on small grants, volunteer effort, and leftover telescope time. Breakthrough Listen changed the math entirely. For the first time, the hunt for signals from other civilizations had real, substantial, reliable funding. The project began operations almost immediately. The Greenbank Telescope in West Virginia, the largest fully steerable radio dish in the world, dedicated roughly a quarter of its observation time to Breakthrough Listen. The Parkes Telescope in Australia did similar work from the Southern Hemisphere. An optical telescope at Lick Observatory in California joined the search, looking for brief laser pulses that might indicate an advanced civilization using light beams for interstellar communication. By 2025, Breakthrough Listen had observed more than 1,100 nearby stars intensively, scanned the entire galactic plane multiple times, and collected more data than every previous SETI project in history combined. The raw data set now exceeds 2 petabytes, roughly equivalent to 10,000 full-length high-definition movies. The project has also pioneered the use of artificial intelligence for signal classification. Machine learning algorithms sift through the data, flagging patterns that look potentially interesting. In 2023, a team using neural networks trained on known interference sources rediscovered 8 candidate signals in older Breakthrough Listen data that human analysts had missed. Each signal appeared to come from a different star system. Each showed properties roughly consistent with what a narrow-band artificial transmission would look like. None has been confirmed as genuinely artificial. Most were eventually traced to subtle forms of terrestrial interference. A few remain classified as unknown, meaning they are consistent with artificial signals but not confirmed as such. These unresolved candidates are logged, flagged, and added to a queue for re-observation. The most interesting finding of Breakthrough Listen may be something else entirely. Not a confirmed signal, but a kind of strong upper limit on what is out there. If bright, obvious, easily detectable artificial transmissions were being beamed at Earth from any of the thousands of nearby stars the project has observed, breakthrough listen would almost certainly have caught them by now. The silence is meaningful. It suggests that our immediate galactic neighborhood is not full of civilizations broadcasting their existence loudly and continuously. This could mean many things. Maybe no nearby civilizations exist. Maybe they exist but use communication methods we cannot yet detect. Maybe they intentionally stay quiet, following a version of Hawking's warning. Maybe their transmissions are targeted elsewhere, not toward our small portion of sky. Yuri Milner's 10-year commitment expires in 2025. The project is currently in the process of renewing funding and expanding to new telescopes. Its legacy, regardless of what happens next, will be the most thorough listening campaign humanity has ever conducted. The sky has not answered yet, but we have never listened better. Not everyone in the scientific community believes we should continue to actively search for signals from other civilizations. A small but thoughtful minority argues that SETI, in its current form, may be a dangerous or pointless enterprise, and that humanity should reconsider its approach entirely. The arguments against continued listening fall into several categories. The first is technological. Some researchers point out that radio waves are a very specific, very narrow form of communication that depends on a technological era that may be brief. Human civilization began broadcasting radio signals about 100 years ago. Already those signals are becoming weaker and rarer as we shift to tight-beam digital communication, fiber optic cables, and laser transmission. The loud, bright radio broadcasts of the 1950s and 1960s are fading. A civilization much older than ours may have gone through the same transition centuries ago. They might still communicate internally, but their signals would be invisible to radio telescopes. If this is true, SETI is chasing a technological phase that lasts maybe a few hundred years in a civilization's total history. The probability of catching another civilization during exactly that phase is small, and gets smaller as the assumed civilization gets older. A second argument is environmental. Some researchers argue that humanity has not yet solved its own existential problems and is in no position to expand its cosmic awareness. Climate change, nuclear weapons, pandemics, and artificial intelligence all pose serious risks to the survival of our species within the current century. Devoting resources to SETI when our own continuation is in doubt strikes some critics as misplaced priority. A third, more troubling argument concerns the consequences of success. The historian David Brin has written extensively on what he calls the silence question. If the galaxy is older than our species by billions of years, many civilizations should have already existed. Yet we observe no evidence of them. This is the classic Fermi paradox, named for the physicist Enrico Fermi, who is said to have asked at a lunch in 1950, "Where is everybody?" Brin and others have proposed that the silence may not be accidental. It may be a survival strategy. The galaxy may contain other civilizations, and those civilizations may have learned, through evolutionary experience, that making noise is dangerous. Perhaps some predatory civilization listens for radio transmissions and eliminates the senders. Perhaps every species that figured this out stopped broadcasting. Perhaps we, by continuing to listen and to occasionally transmit, are announcing ourselves to whatever remains. This argument is speculative. There is no direct evidence for predatory civilizations, but there is also no direct evidence against them, and the Fermi paradox remains genuinely unsolved. The silence of the galaxy has some explanation. We do not know which. A fourth concern involves interpretation. Even if we detected a confirmed artificial signal, what will we do with it? The signal would take decades or centuries to return any reply, meaning real conversation would be impossible. The message content in a foreign code might be permanently indecipherable. The knowledge that we were not alone, without any ability to act on it, could destabilize religious and philosophical traditions worldwide. The scientific community has no agreed protocol for how to announce such a finding, or who would have authority to respond. These concerns have not stopped the search, but they have made it more thoughtful. The people who listen tonight know what they are risking. In all the effort to listen for artificial radio signals, one assumption has dominated SETI for 60 years. We assume any advanced civilization will use radio waves in roughly the same way we do. Narrow bands, specific frequencies, clear, distinguishable signatures that stand out from natural cosmic noise. This assumption might be wrong. Some scientists now argue that we may be listening to the wrong thing entirely. If an extraterrestrial civilization is significantly more advanced than us, they might use communication methods that are invisible to every telescope we currently operate. Several possibilities have been proposed in the last 2 decades, and each represents a potential blind spot in our search. The first possibility involves neutrinos. These are nearly massless particles that pass through solid matter almost without interacting. A beam of neutrinos could carry information across interstellar distances without being absorbed or scattered by dust, gas, or intervening planets. Neutrino detection on Earth is currently in its infancy. Only a few detectors worldwide can catch neutrinos at all, and only from the brightest natural sources like the Sun or a nearby supernova. A weak neutrino transmission from another civilization would be completely invisible to us. A second possibility involves gravitational waves. These are ripples in space-time itself, produced naturally by violent astrophysical events like merging black holes. A sufficiently advanced civilization could, in theory, produce artificial gravitational waves as a communication medium. The LIGO and Virgo detectors, the only instruments currently capable of detecting gravitational waves, are designed to look for natural astrophysical sources. They are not tuned to look for patterns that might indicate artificial signals. Such patterns, if they existed, might be dismissed as instrumental noise. A third possibility involves physics that we do not yet understand. Quantum entanglement, faster-than-light communication through mechanisms unknown to current science, or manipulation of dark matter and dark energy, are all speculative but not impossible. An advanced civilization that discovered a communication method beyond our current physics would be effectively silent to our instruments. A fourth, more modest possibility involves patterns hidden inside noise. Rather than sending bright narrow band signals, an advanced civilization might use a technique called spread spectrum communication. By spreading a signal across a wide frequency range and encoding it below the level of background noise, the transmission becomes almost undetectable unless you know exactly what pattern to look for. Military communications on Earth already use similar techniques. We have no way to search for such signals without knowing the specific pattern in advance. Several researchers have proposed that we should look for unusual statistical properties in cosmic radio noise. If an advanced civilization were using spread spectrum techniques, the background noise in certain directions might show subtle deviations from pure randomness. No comprehensive search for such deviations has ever been conducted. The data may already exist in the archives of projects like Breakthrough Listen, waiting for someone to analyze it with the right statistical tools. A final possibility is perhaps the most unsettling. The signals may be obvious, but we may be misinterpreting them. Every strange astrophysical phenomenon catalogued over the past century, from fast radio bursts to Tabby's star to the cold spot, has been eventually classified as a natural event. What if some of these classifications are wrong? What if one of the anomalies discussed in this video is, in fact, an artificial signal that we have labelled as a natural oddity because artificial explanations are not our default mindset? That question has no easy answer. The universe may already be talking, we may simply be bad listeners. On August 15th, 1977, a radio telescope in Ohio caught a signal that lasted 72 seconds. 49 years later, that signal has never repeated. Every telescope on Earth has pointed at its coordinate. Every advance in listening technology has been applied to that patch of sky. Silence. The wow signal is older than any of the researchers who still hunt for its return. Jerry Eman is gone. Many of the original SETI pioneers are gone. The big telescopes used to search for it in the early years have been replaced, or, in the case of Arecibo, destroyed by structural collapse. The data from that morning in 1977 sits in a climate-controlled archive preserved digitally, waiting for whatever comes next. Throughout this video you have travelled across a map of strange signals. Some have been explained. Some have turned out to be microwave ovens leaking faucets in radio observatories, icebergs cracking in Antarctic waters. Others have been traced to natural astrophysical processes like magnetars, pulsars, and collapsing neutron stars. The universe has revealed itself as a wildly noisy place, full of objects that blink, rumble, flash, and hum in ways we're still learning to interpret. Some mysteries remain. FRB 12102 still repeats on a 157-day schedule that no magnetar model fully explains. The Tau's hum remains undetected by instruments, despite being heard by dozens of people. The cold spot in the cosmic microwave background has no fully satisfying explanation. GPM J1839-10 pulses every 18 minutes from a neutron star that should not be able to pulse at all. The universe keeps tossing up puzzles faster than we can solve them. What this means for humanity depends on how you choose to read the evidence. One interpretation is that the galaxy is lifeless, that we are effectively alone, and that every signal we catch is the product of natural physics, however weird that physics turns out to be. Another interpretation is that the galaxy is full of life, but that life communicates through methods we cannot yet detect, or that it has chosen to remain silent for reasons we cannot easily guess. A third interpretation is that the answer is hiding in data we already have, in anomalies we've catalogued and misunderstood, in whispers we have misattributed to natural processes because artificial processes are not our first assumption. The tools for finding out are improving every year. New radio telescopes in South Africa and Australia are surveying the sky at scales that were impossible a decade ago. The Breakthrough Listen project has sifted through more nearby stars than any previous effort in history. Artificial intelligence is being trained on cosmic data, flagging patterns that human analysts would miss. The next decade will almost certainly produce more anomalies, more mysteries, and possibly, if we are patient and lucky, an answer. Jerry Eman said near the end of his life that the signal he circled in red ink had behaved like a voice, not like static, not like a glitch, like something that spoke, knew we were not ready, and moved on. Whether he was right or not, the memory of that 72-second burst keeps people pointing telescopes at an empty patch of sky, year after year, listening. Somewhere out there, something might still be whispering, "Keep listening."